So this is the last bit on aluminum. It's quite a long section, but in general, it's the least important for you to memorize, especially when it comes to time for the exam. Right? This is all about commercially important alloys and applications and specifics about individual alloy systems. Right? There'll be, I think it's pretty safe to say, you'll see questions relating to this on the exam, but it won't be anything that you have to memorize or know, right? There's nothing that if you don't have a good understanding of the first two parts, if I give you the data, you can't work out or understand what's happening, right? You don't, in fact, all the questions, the way I asked them could probably be answered even if I didn't give you the specific alloy that I was asking the question about, right? Just look at the data, and if I gave you some compositional information, you would be able to work it all out. So we have to start out with the designation. So aluminum is broken up into families by what is the primary alloying element, right? So this system was designated from the Aluminum Association of the U.S. It's slightly different internationally, but we basically have 4 digits. If it's the first digit is a 1, it's pure aluminum, at least commercially pure. The second digit of 2 indicates that the primary alloying element is copper. 3 manganese, 4 silicon, 5 magnesium, 6 magnesium and silicon, 7 zinc, 8 and others, and that primarily for us means the aluminum lithium alloys. The second digit indicates a close relationship. So 5352 should be closely related to 5052 and 5252, and 7075 is closely related to 7475. The third and fourth digit are just a serial number, and they don't have any meaning, right? It just means it's just a kind of a secondary designation. Except in the 1000 series where it indicates the purity. So 1145 means it has a minimum purity of 99.45%, where 1100 would be a minimum purity. This should be 1100, not 1200. 1100 has a minimum purity of 99%. Sorry about that typo. Should be 1100. Okay. You'll also see what are called temper designations along with the alloy composition, right? It tells you that what's been done to it. So F is as fabricated, O is for annealed, right? And this is for wrought products. H means it's been cold worked. T means it's undergone a heat treatment, and these are the primary, right? So H, particularly for non-heat treatable alloys that are in the solid solution strength state, strain hardening is the most obvious way. So H H stands for hard or hardened, and it's the in the strained hardened condition designated by H. The first digit indicates any treatment after cold working. So H1 is cold work. H2, cold worked and then partially annealed. H3 is cold worked and then given a very short heat treatment to stabilize, just to stabilize it, but not to introduce any annealing or larger amount of softening that you would get in the H2 state. The second digit indicates the residual hardening. So H12 means it's a quarter hard. H1 means it's in the cold work state. And it's 2/8 hard, or 1/4 hard. H18 then is fully hard, or 8/8 hard, heavily cold work. So it's equal to about a 75% reduction in the original cross-sectional area. Right? H2, strain hardening and partial annealing. Right? The products are strain hardened more than necessary. Right? So we go over the mechanical properties and then reduced in strength by a partial annealing. H3 tempers will come up again. They're only used for aluminum magnesium alloys. We'll talk about it more in detail when we get to that section. But these tend to soften with time at room temperature after strain hardening. So there's some residual recovery mechanisms that can take place at room temperature. So these are given a short elevated temperature exposure just to exhaust that softening so that the hardness is stable at room temperature. So a third digit can be assigned for wrought products. Right. So you'll get them, you can really look these up. It's not important to memorize or anything like that. So H111 is strain hardened, but less than the amount required for a controlled H11 temperature. So remember, the second digit indicates the residual hardening, right? So H11 would be 1/8 hard. H111 is slightly less than that, right? It's a little confusing. I know. T is the heat treatment condition, right? These are for age-hardened alloys only, right? The most common designations are T4, which is solution heat treated and quenched and then given a natural age, right? So the natural age here means room temperature. So icebox rivets are a name given to aircraft rivets that are 2024 T4. And what they do is solution heat treatment and quench, and then they're stored at cryogenic temperatures. And they're shipped in basically on dry ice. Then when you use them, you let them come up to room temperature, and you only have a short amount of time that you can use them because they will naturally age at room temperature to get the full hardness. So if you let them sit at room temperature for more than an hour or so, they'll be too hard to buck to set the rivet in place. So those are what are called icebox rivets. They will naturally age to their full hardness at room temperature. T5 means we rapidly cool from a processing operation, such as extrusion, and then artificially age. And artificially age means a furnace age at an elevated temperature. T6 is solution heat treatment, quench, artificial aging. T8 is solution heat treatment, quench, cold work, artificially aging. The second digit indicates the amount of cold work. So T85 means solution heat treatment, quench, 5% cold work, and then an artificial age. right? So other designations to indicate stress relieving, right? So if we have X as the appropriate digit, so T451, right? Which means it would be in the T4 state, solution, heat treatment, quench, natural age, and then it's stretch relief by stretching after quenching. So after it's quenched, it would get a strain depending on the shape. Right? If we have extruded rod, bar, shapes, or tubes, we get another one, which means we've done stress relieving plus the degree of straightening and thermal relief that's gone into it. All right, so unless you work with these all the time, you're just going to have to look them up. I can never remember what these are off the top of my head. So if we go through this specific alloy systems now, we're going to start with the non-heat treatable alloys. So these are compositions that do not respond to aging. They're in the solid solution state, and we refer to them as non-heat treatable. So pure aluminum, the 1000 series, right, which is going to have a small bit of manganese in there. The manganese and magnesium is the 3000 series, magnesium 5000, and also the casting alloys containing silicon of the 4000 series. These are the compositions that make up the non-heat treatable alloys, right? Oops. These are sort of the composition ranges that we're looking in. If we look at the magnesium and manganese compositions. Just some example alloys, what they're used for, and what the temper that they're typically used for. We can, here we see aluminum foil, 1145 in the annealed state, and some general properties. Oops. Right. So our strengthening mechanisms are going to be strain hardening and cold working during fabrication, dispersion hardening, aluminum magnesium solid solution strengthening, and both. We can get some precipitate hardening in aluminum magnesium, aluminum manganese magnesium, just like we can aluminum manganese. Going the wrong way here. So the 1000 series alloys, the ones of interest, are commercially pure aluminum, 99%, super pure, high purity aluminum. This would be 4 nines. So it's very weak mechanically, but it's important for use in electrical conductors. In the 60s and 70s, aluminum electrical wiring was quite common, and it ended up being a fire hazard because people mixed aluminum and copper wiring together and had corrosion, which led to resistance fires, essentially. Aluminum foil and architectural products like the window frames in the lecture hall. 3000 series alloys are very important, with manganese as the principal alloying element. The max manganese is typically 1.25%, which is less than the max solubility. This limitation is really because the iron impurity reduces the solubility, giving us large MnAl6 particles, which are going to reduce ductility. right? If we put in manganese closer to the solubility limit, right? The only widely used alloy in the 3000 series is 3003, and this is as sheet, and this is the beer can alloy, right? So we have these fine manganese-containing intermetallics that give us a little bit of strengthening. Strength increases with work hardening. If we add a little magnesium to give us, say, 3004, we increase the strength in the annealed condition, and it increases the recrystallization temperature a little bit. Right, so 3000 series alloys are used in applications requiring sort of medium strength with high ductility. The most important thing is corrosion resistance. So again, beer cans, cooking utensils, and roofing sheet. So if someone has a metal roof, an aluminum roof, chances are that it's going to be 3000 series. 4000 series alloys, the principal alloying element is silicon. Silicon lowers the melting point without producing brittleness, has a deep eutectic. So these are used for welding and brazing alloys, for welding wire and brazing alloys because of the deep eutectic and the low melting point. 5000 series aluminum alloys, right? So magnesium is the principal alloying element, slightly less than 1% to over 5%. Typically, you don't normally go that high because the solvus temperature of the GP zones, right? Adding a lot more magnesium, we get a much higher strength, right? We can get large ductilities out of these systems. They rapidly, for aluminum, work harden with increase in the magnesium content. The problem is stability. We get the formation of beta primarily at grain boundaries, which causes us corrosion problems and cracking problems. So if the magnesium content is higher than 3 to 4%, tendency to form beta phase, precipitation occurs in slip bands and on grain boundaries, and it's intergranular attack, stress corrosion cracking. Right. Precipitation of beta phase occurs slowly at room temperature, but increases with work hardening or as temperature is increased. Remember, we were talking about how this is a problem for the Navy currently with ships in the tropics for a long period of time. We can reduce the kinetics, retard the kinetics of beta formation with the addition of chromium and manganese. Right, this is going to raise the recrystallization temp and also strengthen the alloys. So that means we can get away with a lower magnesium content if we're concerned about beta phase formation. For example, alloy 55454. The magnesium content is only 2.7%, but we can get similar tensile strengths and properties to alloys that contain 4% magnesium, but with much less risk of beta phase formation. These alloys, as I said before, will tend to age soften at room temperature. So our tensile properties decrease with time. So we have, this is due to localized recovery within the deformed grains, essentially room temperature static recovery. So we have the series of H3 temperatures, H3 tempers that have been developed, which give us a short burst of elevated temperature to exhaust all these recovery mechanisms so that we have a stable temperature, stable properties at room temperature. Generally cold work to a level so the hardening is more than is required by the design, annealing to around 150 C for a short period of time. The tensile properties are lowered to a required level, and they're stabilized with respect to time. It's also going to reduce the tendency to form beta phase because we have exhausted the recovery mechanism, so we have a lower dislocation density content. So there'll be less sites for the heterogeneous nucleation of beta. Right? These alloys are really good for welding. 5000 series as a whole are highly weldable, really commonly used for truck bodies, pressure vessels, things that we need to stick together easily. So the heat-treatable alloys, right, are the ones that we typically think of when we rely on precipitation strength. Right, the non-heat treatable alloys, I still talked about precipitates a little bit, but it wasn't the primary means of getting strength. We typically use these in H tempers, hardened tempers rather than T temperatures or heat-treated tempers. So the important ones in the heat-treatable alloys are aluminum copper, aluminum the 2000 series, aluminum mag silicon 6000 series, and 7000 series aluminum, zinc, magnesium, with or without some copper. Just some typical composition ranges, examples, the temper they're used in, some properties and applications. Right? The one I keep bringing up in class, 2024, typically used in the T3, T4, T6. I've never seen it in the T8, even though it's listed on this sheet. But aircraft structures and sheets, this is what I worked with a lot when I was an aircraft mechanic. Okay, so 2000 series based on aluminum copper. Very few alloys are actually based on the binary. They typically have other elements added. But the aluminum copper binary is probably the most well researched because we wanted to study the precipitation sequence and understand the kinetics. So I showed a whole lot of examples of aluminum copper, even though we don't use it all that much. The couple important alloys based primarily on the binary is 2011, which is called free machining aluminum, which is aluminum 5.5 copper, but it also has lead and bismuth in it. And this lead and bismuth are insoluble, and they're soft secondary phase regions. And this means that they form discrete particles when you machine them, and you get nice, clean, easy broken chips instead of long ductile ribbons that wrap around your tools and are a real pain. So 2011 is free machining aluminum. It's only required where you need to get really good surface finishes on machined parts and be able to machine them cheaply. It does not have significant strength at all. 2219 is aluminum 6.3 copper. This is typically pretty close to pure aluminum copper. 2219, it's not on this composition. 2219, we can see it has a little bit of silicon, a little bit of iron. Basically, it has impurity levels of other stuff. Right? We saw that 2011 has bismuth and lead. Right, and this is high tensile properties at room temperature, but it's good at creep, and it has a high toughness at cryogenic temps. And this is really the key property of this alloy. It can be welded, and it's used a lot in space applications, liquefied gas storage tanks in space vehicles, right? Because we want to retain that high toughness at cold vacuum of space temperatures. Strain hardening and aging, so it's typically in the T8 state. The general rest of the group of 2000 series alloys were discovered in the early 1900s. At least the basis of them was discovered in the early 1900s by German scientist Alfred Wilm, right? And this led to the development of duralumin. For those of you, anyone is a fan of the Mistborn series by Brandon Sanderson, you'll remember that duralumin is one of the allomantic metals, which I always liked because it's probably the only time duralumin is ever used in anything. It's sort of an outdated, it was originally developed for development for use on Zeppelins and early aircraft. Its composition: aluminum 3.5, copper 5, magnesium 5, manganese. There's modified versions still in use. There's 2017 for rivets, which, unlike the 2024 rivet, 2024 T4 icebox rivets that I talked about, 2017 rivets can be held at room temperature and still be bucked because they don't age at room temperature. So duralumin was the first, but it formed the basis of a whole suite of alloys. 2014, which has a slightly higher copper content and the addition of some silicon and increased manganese. We get higher strains because of the higher silicon content increases response to our artificial aging, so we increase our precipitation kinetics. Good yield strengths. 2024 is the important one I keep talking about. It has a higher magnesium, 1.5%. Silicon is reduced, and manganese is about the same relative to 2014. What this allows is reduces the aging temperature down to room temperature so they can naturally age. And we can cold work prior to artificial aging, put it in a T8 type temper, and get very high strengths out of these as well. Right? The downside to this alloy is, of course, it's very prone to corrosion. So aluminum, copper, magnesium, like 2024, right? They're still part of the 2000 series, right? But there are strong microstructural effects on fracture toughness and ductility. Generally, for any given 2000 series alloy, they're going to have a much lower fracture toughness than the 7000 series alloys. Primarily because of the size of the intermetallic compounds, right? So if we can reduce the iron and silicon impurity levels so that we don't form them, we can increase the fracture toughness in these, right? And this has led to the development of modified alloys such as 2124, which the 2x24, right, 0 and 1 The second digit tells you whether it's closely related. These have very high limits on the iron and silicon. And then another related alloy, 2048. Our copper's been reduced even further, and the iron and silicon have also been reduced further. And this is a very important aircraft alloy that's still in use, whereas 2024 and 2124 are kind of old-fashioned and a little obsolete at this point in time. Right, but we can see if we look at 2024 and we look at the fracture toughness 22 MPa square root meter up to 37, right? Which means we can have these aluminum copper alloys that perform along the same high toughness values that are in the 7000 series alloys. 2024, the 2000 series alloys generally have better resistance in fatigue than the 7000 series, particularly in this T3 condition where it's solution heat treatment and cold work. However, they don't do so great in stress corrosion cracking. So if we look at this, this is stress corrosion crack velocity versus stress intensity, our K value. We can see we get a rapid rise and then a plateau. So that means if we increase the stress, once we plateau, any further increases in the stress don't really increase our crack velocity. And notice that all these alloys, while they have different stress intensities, the crack velocity plateau is similar, right? So that means we want to rank these alloys in terms of their stress intensity, right? This is where we're going to get the most bang for our buck. If we can increase the stress intensity, we're going to be able to get slow down our crack, right? Because we know they all plateau at about the same. They all plateau at about the same amount. So 2048 in the T851 condition. So what is this 851? Go back and take a look and sort it out. Is the highest, right? Is the most resistant to stress corrosion cracking. Now this, we'll see, I'm bringing this up because when we look at the 7000 series alloys, you'll see a very different behavior. In that case, the stress intensities are all relatively similar, but the plateaus are different. So it'll be a slightly different design strategy when it comes to looking at the 7000 series versus the 2000. Right? So basically what this says is for the 2000 series alloys, if you're at a high stress condition, your crack velocity is going to be about the same no matter which one of these you use. They're a bit, I would say, old-fashioned now, but at the time, they were very advanced. So the Concorde was still an amazingly advanced aircraft, even though it's no longer in service and was designed in the 70s. But Rolls-Royce had to develop a new alloy for it because of the need for creep strength, because of the thermal loading that happens in supersonic flight. So they needed the creep life to be at least 50,000 hours at 120 C, and they came up with this 2618 alloy, which is a forging alloy, which was based on a casting composition, but it's got copper, magnesium, zinc, silicon, iron, titanium, and nickel. Right, copper and magnesium are present to give us the age hardening effects that we know. Nickel and iron form a intermetallic compound, iron nickel aluminide. Right, this is very stable against Oswald ripening and gives dispersion hardening. Silicon was added to increase hardening from GP zones and provide a more uniform distribution of what is known as the S phase, aluminum to copper magnesium. And all of these combine together to give the improvements of crate properties. And in general, this is sort of representative of the strategies for modern alloy design. We're not thinking about one effect, copper magnesium precipitation hardening, GP zones, intermediate phase, second intermediate phase, thermodynamically stable phase. We're doing multiple things at once. So we have different families of precipitates that are doing different duties. And then there's some extra alloying element thrown in there to augment the kinetics of the nucleation and growth of all these different phases to really fine-tune the properties. Right? And so even though this isn't a cutting state-of-the-art alloy anymore, it's indicative of what people do when they're working on alloy design. 6000 series aluminum alloy, right? These are very good weldability, extruded tube that can then be welded, right? This is bicycle frame stuff, right? Right. This is our most common structural alloy that we use, that we encounter, I would say, on a daily basis in terms of aluminum. Very good resistance to corrosion and stress corrosion, cracking. Right. Magnesium and silicon were added to aluminum to form Mg2Si, or slight excess in Si if it's right, and the precipitation sequence goes back to the discovered in the 70s, right? 6063 is the most common alloy. Again, this is your bicycle tube, easily extruded, moderate strength, age hardened, typically in the T6 state, which gives us yield strengths of about 215 MPa. Architectural decorative applications, high purity version 6463 has a lower Fe, which is used typically in the anodized state, often for automotive trim or other cases where you want anodized aluminum. Right, and remember, anodizing is growing an oxide film on it through electrochemical means of a certain thickness so that it appears a certain color. Right, 6061, another really common one. Magnesium and silicon in excess of 1.4%. Solution heat treatment and treated in quench state. If we increase the copper a little bit, we get improved mechanical properties. Adding a little chrome, we get additional corrosion resistance. Right? By adding more copper, we reduce the corrosion. Adding chrome gets us back in there. 6061 T6. Right, and again, these are your bicycle alloys. If they contain magnesium and silicon in excess of 1.4%, They still go through the solution heat treatment and quench stage, but the silicon now is in amounts excess to require to form the MgSi2 particles. We get additional strengthening out of it, but a loss of ductility. The silicon segregates to the grain boundary, causing potential embrittlement. So we add chrome and manganese to counter this effect. Right, promoting fine grain sizes, and inhibiting recrystallization. Right. Sometimes they give it a process where they have a room temperature hold between quenching and aging, and basically it allows the dispersion of precipitates to be fine-tuned because we get vacancy solute clustering. But it really is kind of like a secondary type processing optimization trick, right? We don't need to worry about it too much. The 7000 series of alloys is generally the highest strength age hardening that we can get. They're ternary based alloys, aluminum, zinc, magnesium. They typically also contain a little bit of copper, right? So 7005 is aluminum, zinc, mag, copper, silicon, iron, manganese, chromium, titanium, zirconium. All these different elements in there. They age at room temperature. Strength is generally unaffected by cooling rates from higher temps, which means that you can make big forgings out of them where you can't get a fast, rapid quench. There's a wide range of compositions that'll work for, and temperatures that'll work for solution heat treatment. We get good strength, good weldability with a good recovery of strength after welding, and a big variety of applications. The biggest issue is stress corrosion cracking, and is a huge problem with these alloys, especially in weld regimes. Right, the stress corrosion cracks will just follow right up the weld line through the heat affected zone, and it's been very detrimental to the insertion of 7000 series alloys in a lot of structural applications. So both the strength of the alloy and the susceptibility to stress corrosion cracking are going to increase with the zinc and the magnesium content. Right, but we need to, so we're always looking for a compromise between these two types of properties. All right, in some cases, high strength, but if it's not going to be used in a corrosive environment, maybe we don't need to worry about stress corrosion cracking. There's general design guidelines that say we want to keep the zinc and magnesium content less than 6%, and that'll give us a weldable alloy that does have reasonable resistance to stress corrosion cracking. But also the zinc to magnesium ratio is important, and that our max resistance to stress corrosion cracking is when we have about 2.5 to 3 times the zinc as the magnesium. The problem is the alloys don't actually correspond to this ratio. For other design regions, we have a hard time hitting this balance with structural alloys. So there's been modified heat treatment procedures to give us increased resistance to stress corrosion cracking. air cooling or slow quench rates from solution heat treatment to minimize residual stress. All right, we want to add other alloying elements that decrease our the differences in electrode potentials throughout the microstructure. Right, so we want to try and get phases that are not as good galvanic cells, and then artificially age different heat treatments. This T73 duplex heat treatment is often often used. All right, so we can see that the zinc to magnesium ratio is typically much higher than the 2.5 to 2.7 that we said that we wanted. Right, is interesting. Important one is one of the few Russian alloys that are still around, so it still has the V92 distinction rather than a 7000. Just a curiosity. So aluminum, zinc, magnesium, copper alloys, these have the greatest response to age hardening. These actually came about 10 years after the discovery of duralumin by Rosenhain. They got tensile strengths that were more than 150, 160 MPa higher than duralumin. But again, they were never used because of the stress corrosion cracking problem. But this work really led to the development of alloys, the 7075, right, with compositions here, and 7178 and 7079 with increased tensile strengths. But as the tensile strengths go up, our susceptibility to the stress corrosion cracking also increased. So we need to, when we develop the alloys, need to change processing conditions. So first thing was to eliminate the cold water quench, right? This would give a large degree of residual stress, which would make the finished product more susceptible to stress corrosion cracking because there was already a lot of stress there. One initial solution was to try and use a chromium-free alloy and then a boiling water quench. Just that boiling water quench just sounds dangerous to me. Never seen it. I've never tried it. But I wouldn't want to be doing it. But what essentially developed from all this was this notion of a duplex heat treatment, this T73 temper. So if we did a single aging step at 120 to 135 C, it would follow essentially curve C here, right? You'd get GP zones that would form, right? And it would go through the aging sequences that we talked about before. If you raise it up and you do 170 C, you get eta prime and then eta particles, right? Which are larger. They're not as good at yield strength, at improving the strength as the lower, more finely dispersed particles are, but they give you much better resistance to stress corrosion cracking. But the strength was too low. So instead, a duplex treatment was put together where you would age for a given time to nucleate GP zones, then raise the temperature from 120 to 170 C, and then you would get a refined dispersion of eta prime or eta, right? And you'd get this B curve, and you would have, because the strengthening phase is the equilibrium eta phase, you get a good resistance to stress corrosion cracking and good mechanical properties. So the development of this T73 temper was very important to allow for the introduction of 7000 series alloys into a lot of additional application. The strengths are still about 15% less, but our resistance to stress corrosion cracking. And this led directly to being able to use 7000 series alloys in very large castings. This is the center engine support for a DC engine mount for a DC-10. This was the engine that was mounted on the tail. And this was made out of 7075 aluminum alloy. Right? So, there's no way you could quench this rapidly, right? And not have it distort on you. There's been a lot of subsequent development, different alloys. The specifics of them are not really important to memorize. The T73 and the rationale behind it is the key thing to get out of this. So, remember in the 2000 series alloys, when we looked at the stress corrosion crack velocity, right? They all had the same plateau value, but at different stress intensity. So the design was, well, we can't do much with the crack velocity, so we're going to find the one with the highest K value. Here we can see all the different alloys have different plateaus. So the strategy now is try and find the one with the plateau value that gives you the slowest crack rate for a given stress intensity factor. And generally that happens will be the 775 in the T73 condition. Right? So you can see it gives you much slower stress corrosion crack velocities than 775 in other tempers. Right? And you can see as you get more advanced alloys, very high strengths, but really poor stress corrosion. Resistance. Sorry, I'm getting a little tired. It's late at night. Well, everyone is asleep. The kids are asleep, and I'm recording the lectures for you guys. Trying to talk quietly so I don't wake them up in the hotel room as they're coming with me to New Mexico. The next family is the aluminum lithium alloys. These are 8000 series and some 2000 series where we have aluminum, copper, and lithium. And aluminum lithium has some primary advantages. We can reduce the density. We can increase the stiffness. So there's been a big drive, and there still is, and it hasn't been completely successful, to use aluminum lithium alloys to replace the 2000 series aerospace alloys. Right? So the 2090, 2091, 8090, and 8091 are very important alloys in this regard. Problems tend to be that aluminum lithium binaries suffer from low ductility and toughness. Right? We have severe strain localization from cutting these coherent delta prime particles by dislocations, the L12 structure, aluminum 3 lithium. Right? So anytime we have strain localization, we have issues with cracking. So we get cracking along boundaries. So we want focused on development of including solute elements that will form additional precipitates that are capable of dispersing slip more homogeneously. Right? It's the same story that we keep talking over and over again. Anything that localizes, that allows slip to localize, is going to be bad for failure. Right? We want to have a good dispersion of fine precipitates to give us the yield strength, but we don't want stress to localize on further plastic deformation. Aluminum, lithium, copper. Copper has the effect of reducing the solubility of lithium in aluminum, so we get a higher volume fraction of the delta prime and co-precipitation of other phases. GP zones and theta prime that we get in aluminum copper alloys. If we have low copper concentrations, we get this T1 phase, aluminum to copper lithium plus delta prime. Right, this T1 is not useful in dispersing slip, though. Aluminum, lithium, magnesium. Magnesium also reduces the solubility of lithium. Right, so we get a maximum volume fraction of delta prime for a given lithium concentration. The main role of magnesium, though, is going to be solid solution strengthening. Right? If the magnesium gets above 2%, though, we can form these aluminum to lithium magnesium. These are non-coherent cubic, usually on the grain boundaries, and they have an adverse effect on ductility. So we have to be careful with how much magnesium we add. But it's a good way of increasing our volume fraction of the delta because it reduces the solubility of lithium. Aluminum, lithium, copper, mag. We get co-precipitation of several phases in addition to the delta prime. There's this S phase, which is a very hard phase, aluminum to copper mag, not cut by dislocations, gives us a very good homogeneous slip. There's also an S prime, or an intermediate phase during the aging sequence, but the S tends to nucleate preferentially on dislocation. So we can make the distribution of S phase more uniform by cold work prior to aging. So we have a more uniform set of heterogeneous nucleation sites. The aging sequence is alpha, cold work, delta prime plus S prime, goes to delta prime plus S. But then T1 phase, remember the aluminum to magnesium lithium can also form. So you need to get the compositions just right so you get the phases that you want. Sometimes zirconium's added. Zirconium is interesting because you get aluminum 3 zirconium that precipitates out first, which the delta prime phase can actually nucleate homogeneously on the aluminum 3 zirconium particles. Right? So these are this is aluminum 3 zirconium are roughly 20 to 30 nanometers, stabilizes the grain structure, disperses slip. So all in all, it's a pretty good alloying composition. So just some of the different alloys and the compositions. Properties that you get out, right, and you can see we get pretty high yield strengths, right, with reasonable fracture toughness, right? So you can have high strength alloys, but you can also have damage tolerant alloys, right? 8090 T81 with, look at very high fracture toughnesses. That the trade-off is then we reduce our yield strength and our ultimate tensile strength in these alloys for the trade-off in toughness. Okay, so that's it for the wrought alloys. Cast aluminum alloys are primarily used in the automotive industry. right? These are a replacement for cast engine blocks and engine cylinder heads. So we have a very high strength to weight ratio. Service temperatures are now above 200 C, increased thermodynamic efficiency of the engine. So cast alloys for automotive use tend to be optimized for tensile creep and fatigue strength. And these alloys are going to be aluminum, silicon, copper based. We have two main failure modes, low cycle fatigue and high cycle fatigue. The low cycle fatigue is really thermomechanical fatigue. This is from engine start and stop cycles. When you start the engine, it gets hot and expands. And then when you cool it off, you have contraction. But of course, it doesn't expand uniformly. You have different mounts holding different components in place. So there's stress, thermal stresses associated, and mechanical stresses associated with this. And then the high cycle fatigue is the results from vibration coming from variation of pressures within the combustion chamber. So you can figure if your engine's running at 2,000 RPMs and you run it for 10,000 hours, you're in the range of 10 to the 8, 10 to the 10, 10 to the 10th fatigue cycles on critical engine components. Aerospace applications, landing gear castings, we want high strength and high toughness in wheels, high strength, high tensile properties and machine abilities. These tend to be aluminum copper based without the silicon additions. And then for purely decorative low stress components, aluminum are purely aluminum silicon because these are the easiest to cast. So decorative grills and things like that. The cast alloys have a slightly different designation than the wrought alloys. Instead of the thousands, these are the have 3 plus a final X after the decimal point that indicates the final form. So pure aluminum, copper, silicon, with copper and mag, silicon, magnesium, zinc, tin, other. 6,000 is unused. Most of the advanced alloys are 3,000 aluminum silicon with additions of copper and magnesium. And it's because for castability and strength, this is where the development is. Right? Silicon makes things very castable, but without the other alloying elements, you don't have the strength that you need for high-tech applications. So 319 is an alloy that's commonly used in cylinder heads and engine blocks. Right, it has a nominal composition of 7% silicon, 3.5% copper, and 0.25% magnesium. So the general features are we have aluminum dendrites, eutectic silicon regions. We have Al2 copper, so we have theta and theta prime phases, and a set of complex intermetallics with the S prime phase and this so-called Q phase, right? And a whole suite of other potential intermetallics. We also have porosity, and we have the secondary dendrite arms, and a key property here is the secondary dendrite arm spacing. Here we see the theta phase, eutectic silicon, and a different intermetallic, in this case aluminum 15, iron manganese 3, silicon 2, that's formed here. It also looks to have a dendritic-like structure. So as cast, these microstructures are pretty complicated. The solidification rate greatly affects the coarseness of the microstructure, right? So you can see compare the dendrite, secondary dendrite arm spacing and alloy that in a sample that's been solidified over 17 seconds versus 320 seconds. Right, the scale bars are the same on these, so you can see the regions of eutectic silicon is quite higher. The porosity, we don't see as many large pores, and the fraction of the theta phase. Right, I don't see you see a couple spots here, here. Right, this is the equilibrium theta. You can see much larger regions in the slower cooled. So it probably doesn't come as any surprise to you that the solidification time directly controls some properties. Here we see yield strength and the different aging curves for a rapidly cooled versus a slowly cooled sample. And you see we have a much lower aging time and higher yield strength in the rapidly cooled, right? So the strength is primarily controlled by solid solution strengthening and the evolution of the theta prime phase, right? So the formation of large fractions of primary Al2Cu, or the theta phase, is going to dilute the remaining alloy of copper, right? So we have less of a driving force and less solid solution strengthening, right? Because we have less copper in solution, so we're not going to make as fine a dispersion of the theta prime phase. So the solidification directly influences the strength of the final component. All right? And what's interesting, this is a good exam question. If we look at the yield strength as a function of aging time for different aging temperatures, we see very different behavior. The question is why, right? And it's really differences in the precipitation type, the precipitation sequence, right? Where are these aging temperatures relative to the GP zone solvus temperature? Right? So if we think about 150C, if we get a fine dispersion of GP zones and we go through the sequence, we're going to get a different result than if we age at a higher temperature and go right to theta prime or theta, which are going to form in coarse regions, primarily at grain boundaries, or existing Al2Cu particles. Right? So different aging is going to give us very different microstructure as well. Right? So here's our theta prime structure. Right? Here we can see nucleation heterogeneously on a dislocation, and then at different aging times. Remember, the theta prime forms as plates in these. Right? And so we can break it down as to what are the different contributions, the intrinsic strength, GP zone solid solution strengthening, the precipitates, and then the contribution from all of these is overall. Right? So this, as we grow other phases, the contribution from our solid solution strengthening and GP zones will decrease as we get a distribution of our intermediate and equilibrium phases. Right. So a big problem with these casting alloys is dimensional stability. Right? So microstructure evolution causes dimensional instability. How? Right? So if we reduce the copper in solid solution, we're going to decrease the alpha aluminum lattice parameter, fairly negligible effect. So precipitation of theta prime from GP zones, right? This is going to cause a increase in growth, and then precipitation of theta from the theta prime is going to decrease growth. So if we look at the percent dimensional growth, if we age it at 100C, it's pretty stable for a long time and then increases at the end. 180C, we nucleate theta prime and we get a large dimensional change. At 250C, theta prime, then we nucleate theta and it shrinks again. So it grows and then it shrinks. Right? In the overage state, we can see that we shrink after a long thermal exposure. Right? So this is this T7, it's given a stabilizing treatment. Right? We give it a high temperature to sort of exhaust this, so we have so we're more stable at longer periods of time. Right? Describing what's happening in each graph, right? This is another easy type of exam question. Right? If we look at what happens under different temper and treatment designations, we get different curves with respect to the thermal exposure. So why is this important to consider, right? If we're using this in an engine casting, it's bolted in place, right? Even if the engine, the heads are bolted to the block, right? And if they expand at different rates, we're going to get different stresses. This is going to impart big loads. We also have other things mounted to the engine block, not just the cylinder heads, right? So this is a big cause for fatigue, right? We have stresses and thermal strains. This porosity is very detrimental. Real high-end components can undergo hot isostatic pressing to seal up this shrinkage, right? The solidification shrinkage in aluminum is about 6.5%. So this is pretty high. In titanium, it's only 3%, 4% in nickel superalloys like Inconel 718. Right? So with this fatigue, right, we have cracks that can nucleate at these pores. Fatigue is a real problem here. But with hipping, we can really push these curves out quite a bit. All right, and these are what we would say is these are the low stress. These are the thermomechanical cycling fatigue samples, right, that come from the number of times you start and stop your engine. This isn't the high cycle fatigue of the vibrations, right? So chances are you're not going to start your car 100,000 times over the life of your vehicle. But if we have a high stress state because of shrinkage and microstructure evolution, it might not be out of the realm of possibilities that you might have 10,000 engine starts, right, rather than 1 million. Right. So again, this is just the difference in fatigue properties as a function of the different heat treatments that we have that can directly be tied back to the precipitates that you get, theta versus theta prime, the spacing of 50 nanometers versus 300, right? So a finer dispersion of particles, we have a higher cycles to failure for a given stress, right? So basically, the end is at the end of in this T7 condition with the theta that are farther apart, right? It's easier to get dislocation pileups and stress concentrations, leading to the fracture of intermetallics and initiate a crack. So what we see in this curve is all crack initiation behavior due to the changes in microstructure. Again, memorizing exactly what this is not important. What is important to remember is that there's a relationship between the microstructure and the performance, and that we can alter that by the processing, right? That's the take-home message. If that's what you get out of this class, I'd be happy with that, right? Okay. And this is just this talking about more about the low cycle fatigue and looking at the dimensional stability, right, in the engine blocks. And so when people design components, they actually run models where they take the microstructure evolution into account, and how is the stress state in the engine block going to change as a function of the in-service operating conditions, right? And so that wraps it up for aluminum. We'll be beginning steel when I get back after a little bit of prep for the first midterm.